Good morning, students. In previous period, we have discussed about the rectilinear flow of heat along a metal bar and also have discussed the three cases of the rectilinear flow of heat. That is, first case is before the steady state is reached. Second case, the heat lost by radiation is negligible, and third case is after the steady state is reached. Now, in today's period, we will discuss the methods of radial flow of heat. The first method now we are discussing is the spherical shell method. In this method, we will consider two spherical shells A and B of radii R1 and R2 respectively. Let a source of heat is electric heating element be placed at the center O of the cell. The heat is conducted through the cell from inner to outer cell. The temperature of the inner and outer cell be theta 1 and theta 2 constants after the steady state is reached, as shown in the figure. Consider an imaginary cell of radius r and thickness dr having temperature of theta and theta plus d theta on its inner and the outer surface respectively. The quantity of heat conducted per second through this cell is given by Q equals to minus Ka into d theta by dr. This is equation number 13. Since area of the sphere is given by A equals to 4 pi r square, keeping the value of area in above equation, then equation 13 becomes Q equals to minus K into 4 pi r square into d theta by dr. Now rearranging this equation for as dr upon r square equals to minus 4 pi k upon q into d theta. Integrating both sides with their respective limits and remembering that q is independent of r, we get integrating left hand side from the limits r1 to r2 dr upon r square equals to minus 4 pi k into upon q into integration of dr from q1 theta 1 to theta 2. Here in this integration sign, minus 4 pi k upon q is a constant and hence it is taken outside the integration sign. Now integrating the left side, we get the integration of r square is minus 1 upon r, and putting the limits, then it becomes 1 upon r1 minus 1 upon r2 equals to minus 4 pi k upon q into q2 minus q1. After integrating the above equation and putting the limit values and rearranging the equation, we get 4 pi k upon q into theta 1 minus theta 2. Now rearranging the above equation for the value of k, this can be written as k equals to q into r2 minus r1 upon 4 pi r1 r2 into the bracket theta 1 minus theta 2. This is equation number 14. From this equation, the value of conductivity k can be calculated. Now we will discuss one case, that is the temperature distribution in the spherical shell may be obtained. The value of q from equation 13 and 14 we get minus k equals k 4 pi r square d theta upon dr equals to 4 pi into the bracket theta 1 minus theta 2 bracket close into r1 r2 upon r2 minus r1. This is the value of q from equation 13 and equation 14, and hence we have equated these two quantities, or can be written as d theta equals to theta 1 minus theta 2 into r1 r2 into dr upon r2 minus r1 into dr upon r square. Integrating this equation on both sides, therefore we get integration of d theta equals to theta 1 minus theta 2 into r1 r2 upon r2 minus r1. This quantity is a constant and hence it is taken outside the integration sign, and the quantity which we are integrating is dr upon r square. Its integration is theta equals to minus q theta 1 minus theta 2 into r2 minus r1 upon r2 minus r1 into minus 1 upon r plus c. This is equation number 15. Now in order to obtain the value of constant c, we have where c r equals to r1 and theta equals to theta 1. Therefore, putting these values r equals to r1 and theta equals to theta 1 in the above equation, we get theta 1 equals to theta 1 minus theta 2 into r1 r2 upon r2 minus r1 into 1 upon r1 plus c. Therefore, c equals to theta 1 minus theta 2 into r2 upon r2 minus r1. Substituting it in equation 15, we get. Now we have to put this value of c in equation number 15, and therefore we can get the value of q equals to in the bracket q1 minus q2 into r1 minus r2 r1 into r2 upon r1 into the bracket r2 minus r1 plus theta 1 minus q1 minus q2 into r2 upon r2 minus r1. Now, solving this equation and taking 1 upon r2 minus r1 common, and we get theta equals to 1 upon r2 minus r1 into the bracket theta 1 minus theta 2 r1 r2 upon r plus r2 minus r1 into theta minus theta 1 minus theta 2 into r2. In the next step, we'll solve the brackets. Now 1 upon r2 minus r1 into the bracket theta 1 minus theta 2 into r1 r2 upon r plus, now solving this bracket means multiplying by theta 1 to this bracket r2 minus r1. Therefore it becomes r2 into theta 1 minus r1 into theta 1 equal minus theta 1 r2 plus theta 2 r2. Now cancelling the same terms from the second bracket, and we can arrange this equation theta equals to 1 upon r2 minus r1 into the bracket theta 1 minus theta 2 into r1 r2 upon r plus theta 2 into r2 minus r1 into theta 1 bracket close. This is equation number 16, and the equation 16 gives the temperature of the spherical surface of the radius r. In this way, we have discussed the method of spherical cell method and its case. Now in the next period, we will see the next part.